Lesson 7-8 is about factoring special products. Now, you've talked about special products before when we were multiplying in the first sort of half of this chapter. We talked about the difference of two squares and the perfect square trinomial. And so today, like we have been for the last few days, we're going to go in reverse and see how we would factor those. And here's the bottom line. The difference of squares is the easier pattern. So if you recall, just to do a little example here, let's say that we had two binomials that were almost the same, but the signs or the operations were opposites of each other. So it was the first two terms were the same term, the last term were the same term, but one was a sum and one was a difference. So when we noticed when we were multiplying these in the first half of the chapter is that as we worked the distributive property or FOIL or box method, and we distributed the x here in this case, x times x gave us x squared, and then for the outers we would get a product of negative 5x here. And then when we went to do the second set of distribution, we had a positive 5x and a negative 25. And we started to realize these two middle terms were exact opposites. Okay, and so when we went to combine these, they actually completely canceled each other out. And we were always left, as a result, with the square of the first term and then a minus or a negative perfect square of the second term. And when we learned this initially, I told you, hey, it might not seem like a big deal, but if you know it, it's going to save you some time now, and it's going to save you a whole lot more time later. And for this one in particular, I actually have mentioned in the past, it's pretty critical. It's a great, fast, easy rule, but the catch is you have got to be able to recognize when you have a difference of squares when you're factoring. So that is where we are now. I promised you back then, in a few weeks from now, it would really pay off to be able to identify these, and that is where we are. So we're going to start with difference of squares. That's our first special product, and you have seen it before when we were going in this direction, and so now we're going to practice factoring it out. Now, like I said, this is the one that is very simple but very critical, because our difference of squares is not a trinomial. We are not going to have the magic number option here. Okay, so if I say, hey, factor this, okay, I want you to notice a couple of things. It doesn't have a GCF. Okay, and it is also not a trinomial where we could just do our magic number trick and work it out the way that we've been doing for the last several days. So you genuinely need to be able to see this and recognize that what you have before you is a difference, right there, subtraction, of two perfect squares. And you have to just know that even though it might appear very simplified and maybe that they don't have anything in common, that this does factor. And that it is always going to factor to two binomials with opposite signs in the middle. And in each of these, it's going to be the square root. So the square root of s squared is just s. So that means that this was s times s. And the square root of 49 is 7. So this was positive 7 and negative 7. Okay? So, and that's it. And you have fully factored it and you're done. So is it easy? Yes. As long as you know your perfect squares or you have a calculator nearby, you're going to be okay. But what's really sort of the challenge to this is just that you have to be able to see this and just know that that's the pattern. There's no trick or computational sort of steps to get there. You just have to be able to see it and know, oh, that's a difference of squares. I know how that factors. Okay? And so if you see this guy here, you want to be able to say, oh, it's a difference of two perfect squares. So that factors to x plus 5, which are the square roots of those. And then the other is the same, but with the opposite operation. We're going in this direction now. Same thing here in this example. If you start off with a difference of x squared and 9, you just have to know, see it and say, oh, that's a difference of squares. So I can rewrite it as x plus 3 times x minus 3, and that is how it factors. Once you catch on to that pattern, it certainly is quick and easy, right? Like I said before, the challenge is just knowing that you have to know it. So let's try number 2. You've got the difference of two perfect squares here. So we know that that factors to t, which is the square root of t squared, plus the square root of 81, which happens to be 9. And then the exact same thing, but with a subtraction in the middle. And again, what is true about these is that you could still FOIL these and check your answer. You should be able to FOIL these or multiply them like I did in my example here and see that it works, okay? Same here, 16 is a perfect square, x squared is a perfect square. I have my difference in the middle there, so I know that this is the result of multiplying 4, which is the square root of 16, plus x, which is the square root of x squared, and then another one just like it, but with a subtraction. So the difference of squares always have different signs. It doesn't really matter if you put the plus or the minus first. I tend to put the plus first, but that's not a hard and fast rule. But what does matter is that they are different, okay? So let's try one with a couple of coefficients here. Even though this has a 36, 36 is still a perfect square, so is h squared. And 101 is a perfect square. And since this is the difference of two perfect squares, we can definitely factor that. So the square root of that first term plus the square root of 121, which is just 11. And then I have another one just like it, but with the opposite sign. Okay. So try numbers 4 and 6. See how that goes. See if that feels pretty good. Okay. All right. We are actually not going to stress about this. This shows you that, you know, if this is a perfect, I'll do one as an example, but we're not going to spend a lot of time on them, and I'm not even sure that we really have them on the practice, but just so you can see it. Technically, what we're saying here is this math would not be very pretty, especially if you didn't have a calculator. If you didn't have a calculator to actually work this out, you'd have to really by hand figure out, okay, what's 57 squared, 57 times 57 minus, and then that guy squared. But since they are a difference of two perfect squares, we can use our pattern. So the square root of 57 squared is just 57 without the power. And the square root of 53 squared is just 53. And in the other one, it would be the same two numbers, but subtracted. And then this would be a lot easier to work out. 57 plus 53 is 110. And the difference here is 4. And then I would just multiply that and pretty quickly be able to calculate, oh, that's 440. Okay? And then, you know, it just lets you use the same rule to kind of work out problems that would otherwise be pretty cumbersome. And I'm just going to show you here on the calculator that it does work. If I had checked it, if I did have a calculator and I did 57 squared minus 53 squared, there it is, 440, right? But that difference of squares lets me calculate it in a much easier way, okay? All right, so now that you know the pattern and you've practiced it, as always, we then bridge it with the whole point of this, which is using the zero product property to solve, okay? So if I want to solve this equation here, I can say, all right, this is a difference of two perfect squares, so I know this factors to x, which is the square root of x squared, plus 12, which is the square root of 144, and then another similar binomial, but it just has a minus. And since all of that is equal to 0, then we can use the zero product property to find the solutions. So if this times this is 0, we know that that is going to happen if either this binomial is equal to 0 or this binomial is equal to 0. And then we solve each one of these. So one solution is x would be negative 12. The other solution is that x would be positive 12. And those are the roots, the zeros, or the solutions. If it's not equal to 0, look at number 11, then of course that's always our first goal, right? We don't want to work this the way it is right now, so we want to be able to move this 49 to the left side. So we'll subtract 49. And now it'll be subtracted on the left. Nothing will be left on the right. And then I can recognize, well, 9. This is, again, where it really pays off to know that numbers are perfect squares. So if you want to have a little list of your perfect squares from 1 to 20, that would probably be very wise, unless you really genuinely have them all memorized. So if we solve this guy, I know 9 is a perfect square, I know 49 is a perfect square, and I know the square roots are 3 and 7. So 9y squared has a square root of 3y. 49 has a square root of 7. And then the other will be the same thing, but with the opposite sign. And then we'd be able to set each one of those equal to 0 and find our solutions. And solve each one of those. So for these, we would have to, like on the left side, we would subtract 7 on both sides. We'd get that 3y is equal to -7. And then we divide by 3. And since that doesn't divide evenly, that is not a problem. We'll just leave it as a fraction. So -7/3 is one of our answers. And on this side, we would add 7. Something similar is going to happen. Just, signs are just slightly different. And then we'll have 3y equals +7. We'll divide by 3 on both sides. And then the other solution is also +7 divided by 3. And we'll just do that as a fraction. Okay. All right. That is difference of squares. Okay. It's easy if you know your perfect squares, but it's critical. And I said that back a few weeks ago, and I'm here absolutely preaching it again. If you don't catch it, you don't realize that this factors any other way, because it doesn't appear to have, a lot of times it doesn't appear to have a GCF. It doesn't fit that magic number trick. So you just have to see it and know that that is what you have in front of you, a difference of squares, and that it factors this way. Okay, so that's the first special type of polynomial or special product. The second one is the perfect square trinomial. We talked about this one already as well. It's when we're multiplying something times itself, okay? And instead of the middle terms canceling, they doubled up. So if you remember that pattern, if we had something like x, plus 4, and that was squared, if you knew the pattern, it saved you from having to expand and FOIL. If you knew the pattern, you knew that it was going to be the first term squared, the product of these doubled, so this would be 4x, and if I double that, I get 8x. And then at the end, it would be the square of that 4. And so we knew to go in this direction, and so today we're just going to practice going in this direction. Okay. Now, like I said, this one really is more of a shortcut still. It's just going to save you even more time than it did the first time. The good news about the perfect square trinomial, right, is that if you recognize it, you save yourself all of that work with the magic numbers, and especially later on if it has a leading coefficient, it saves you all the work that we've been doing as far as finding the magic numbers, splitting the middle term, factoring by grouping, all of that work if you recognize that it is a perfect square trinomial. But the good news on it is if you don't recognize it, you can still get the answer. It's not like the one we just did where if you didn't catch it, you missed the boat and you get it wrong. Here, it would just be like you would just do all of that work. Because it's a trinomial, you still always have the option of doing that 4-step method that you learned a few days ago. Okay, so we're going to practice it with the pattern, but that's the silver lining for this one. Miss it, it is just going to be a little bit more work. Okay. So let's talk about how we recognize. Okay, remember what the pattern is, because that's what's behind all of this. So typically what I do is, if I'm looking at this and I check the first and last term, and if these guys stand out to me as perfect squares, okay, then to me it's worth checking. Now I'm going to be very, very clear. Please listen to what I'm about to say next. Just because the first term and the last term are perfect squares does not mean that the whole thing is a perfect square trinomial. Okay, I want to be very clear about that, and I'll give you an example of something that has perfect squares on the ends, but it is not a perfect square trinomial. So take this trinomial for just a moment. Okay, if I were to do this with the magic numbers, I'd be looking for 2 factors of 16 that combine to 10. Now, this is a perfect square. X squared, that is a perfect square. 16 is a perfect square, okay? But the numbers that work here, that multiply to 16, but add up to 10, those numbers are 8 and 2. And so the two factors that made this are x plus 8 and x plus 2. That is not a perfect square. That is not the same thing times itself. These are different. Okay, so yes, this was a perfect square. Yes, that was a perfect square, but that doesn't guarantee a perfect square trinomial. The middle term still has to be the right pattern. Okay, so don't just, now, if you check that these are perfect squares, it's worth checking because it will save you some time, but it doesn't guarantee it. Okay, and that's a good example of a perfectly good trinomial that is not a perfect square. It's not the same thing times itself. These are different. But the result just happens to have perfect squares on the ends, okay? So this is what we're always checking for. If these guys are perfect squares, good, let's check, okay? Then we always want to check the middle term. That's the main idea. So what is the square root of x squared? Just x. What is the square root of 64? 8. The question is 16 the product of those two things doubled? Right? That's what we're always checking. Is that 16 in the middle equal to 2 times those two numbers that we just agreed on? And if the answer is yes, then we can say, oh yeah, that's a perfect square, and I don't have to go through the magic and the splitting and all of that. I just know that this is the result of x plus 8 times x plus 8 again, or in other words, x plus 8 to the second power. And I can factor it a little bit faster. Okay, let's try number 13. So on number 13, I see a perfect square here and here. Those are perfect squares. The square root of r squared is r, and the square root of 169 is 13. So the question is negative 26, actually, it's going to just have a negative in the middle, so don't even worry about the sign. Okay, like 26 is what we really care about. So is 26 the product of 2 times these two things multiplied? If the answer to that is yes, then that's a perfect square, and we just know it's going to be r. That middle sign is what always goes in the middle, and then the 13. And then we basically have two factors that are the same. So is r minus 13 times itself, or in other words, r minus 13 to the second power. It pays off even better when you have leading coefficients, because we already know that when we have leading coefficients in a problem like this, there is no GCF. If I were going to do this the long way, I would be doing 36 times 49, which is probably something very big, for factors of that add up to 84. Okay, and yes, you can still do that. Okay, you're always welcome to do that. But if you start to be, if your antenna start to be like, wait a minute, that's a perfect square and that's a perfect square, let me see if I can save myself some time here, then let's try it. The square root of 36c squared is just 6c. The square root of 49 is just 7. Okay. The question is this middle term, 84c here, the result of double or 2 times the product of these guys? That's the question. So is 84c the result of 2 times 7 times that 6c? So we just multiply those two square roots. And if that's the case, we hit gold, right? And we don't have to go through all of those steps that I just mentioned. So let's find out. If we do this, 7 times 6 is 42, and 42 times 2 happens to be 84, and we do have that C. So this did work out, and that means that instead of going through all of that work, I can just say, oh, this is basically 6C, my middle sign goes in the middle, and then my 7 times itself, so I can write it twice, or just put that power on it, showing that it's times its own self. And then I can, and again, if you miss it, then you just go through that longer process, and you do your magic numbers, and you find, you pull the calculator if you need, and you split the middle term and you factor by grouping, you still get to the answer. This is just a lot faster. But remember, on the other one, on this one, there is no plan B. There is no other option. You know, you've got to look at it and be able to tell, yeah, that's a perfect square. I mean, that's a difference of squares. And I just have to know it. I just have to know it. I have to know the pattern. I know it'll be the square root of each one. And one will be plus, one will be minus. Okay? All right. So try number 15. And then we'll try a couple here solving and a word problem. All right. So if you tried 15, hopefully you got that one right. Let's try 16 now. So the only thing, again, this is bringing together is now that you know the pattern. After you factor it, once it's equal to 0, after you factor it, you make sure that you find the zero product property and find your solutions. So let's look at number 16. I think this might be a perfect square, but let's check. That's a perfect square. That's a perfect square. The square root of c squared is c. The square root of 49 is 7. Is this middle term, that 14c, is that the result of 2 times the product of these? So 2 times 7 times c. The answer is yes, right? 2 times 7 is indeed 14c. So this is true. And therefore, this is a perfect square trinomial. And we can rewrite it factored as c, the middle sign, and then our 7. And we know we have 2 identical factors. So the answer is going to be one of those repeated roots. Okay, since it's this times itself, we don't necessarily have to solve it twice because it'll be exactly the same thing again. We just have to set it equal to 0, solve it once, and acknowledge that that is a repeated root. Okay, so 0 minus 7 is just negative 7. So c would be negative 7, and that would be a repeated root. Okay? That would be our answer right there. Let's try one of these other ones that don't look quite as fun or pretty. Let's try 19. I like that one. So the first thing is it's not equal to 0. So y'all know the drill. It's always got to equal to 0 before we start to use the zero product property. So I'm going to move that k squared to the left so that all of my terms are on one side and it's equal to 0 on the other. Cancel. We now have k squared minus 6/5 k plus 9 over 25, and that is equal to 0. Okay? Now you can work this out as fractions, and you're welcome to do that. And so you could say, hey, this is a fraction, but I still see perfect squares like 9 and 25, and if I take the square root of 9 and 25, the square root of that is just 3/5. And the square root of k squared is just k. And right here in the middle, the question is 6/5 k just the result of 2 times the product of those 2 square roots? And the answer is yes, because 2 times 3 is 6. So that's 6/5 there, which is what we had. So yeah, the answer is yeah, that works. And since it's a perfect square, then we can just write it in factored form as k, the middle sign, which is a subtraction here, and then the 3/5. And we have 2 identical factors equal to 0. And then all we have to do is set that particular binomial equal to 0. Since it's the same times itself, we only have to solve it once and then just say that it is a repeated root. So we'll set this equal to 0. To solve it, we'll just add that fraction. So k ends up being equal to 3/5, and it is a repeated root. I'm going to abbreviate it since I am running out of space here. Okay, so that is the perfect square trinomial pattern. Great shortcut, but not necessarily like absolutely as critical as the difference of squares. Okay, so let's take a look at a word problem here, and we'll probably finish off with this one and maybe try the next one in class. It says the dimensions for a rectangular prism are x plus 1, x plus 2, and 4 feet. So I'm just going to kind of sketch. Y'all know the drill. If they don't provide it, draw your picture to help you understand what's going on in that question. So there's my box. It doesn't have to be amazing, but I know that the dimensions are x plus 1, x plus 2, and 4. So that's our length, our width, our height. The volume, they tell me, is 24x minus 1. What is the value of x? So remember, for a rectangular prism, volume is the result of the length times the width times the height. Okay? That's how you generate that volume. So this here is a result of multiplying that 4 times that x plus 1 times that x plus 2. And that resulted in this volume right here. And we want to solve this for x. Okay, so let's get started because we've got our work. Although this looks factored, we've talked about this many times now. If it's not equal to 0, these are not the factors we need, and therefore, they're not very helpful to us. We're going to actually just multiply all this in. So maybe I'll start by distributing our 4 into this first one. And then once I have it like that, then I will multiply these two together. Using distributive, FOIL, box method, whatever you like. So 4x times x, 4x to the second, 4x times 2 is 8x. And then our inner terms, 4 times x is 4x, and 4 times 2 is 8. And then, of course, as usual, there's a couple of like terms, so we really end up with 4x to the second plus 12x plus 8. And that is equal to 24x minus 1, which was the problem. So now that it's multiplied together, we are going to combine we're going to combine everything on the left. We're going to move these guys over. So I'm going to subtract that 24x and line it up with my like term. And I'm going to add that 1 and line it up. That's going to allow me to cancel both of those. And I'm going to have a new polynomial here. So now coming up here to have more room, I still have 4x to the second. Here in the center, positive 12 and negative 24 is a negative 12x. And at the end, 8 plus 1 is 9. And that's equal to 0. And then I can factor this. These are the one that, this is what we're interested in, and it's equal to 0. And these are the factors that are going to actually help me find x. So, but I realize, hey, this is a perfect square, that's a perfect square. The square root of this is 2x. The square root of that is 3. And is the middle here the product of these doubled? The answer is yes. 2 times 3 is 6. If I double that, I get 12. So I can quickly do this part of it and say, oh, this is going to be 2x, my middle sign, and the 3, and I basically just have two identical ones that are equal to 0. So I only have to solve this once. It's a repeated root, so all I have to do is add 3 on both sides, and that gives us 3, and then divide by 2. And that tells me that x is equal to 3 over 2, or 1.5. And this was in feet, so this must be the dimension or the x value that makes that volume true. That's your x value there. We'll just finish up with that one, and we will leave 21 and 22 for class tomorrow.